Hello future engineers. In this video, I'm going to discuss two-force, three-force body and composite body principles applicable to 2D equilibrium problems, 2D rigid body equilibrium problems. Hello future engineers. In this video, I'm going to discuss two-force and three-force body principles as well as interconnected systems or composite body principles. And this is one case with three cases, three explanations. So first I'll discuss two-force and three-force body principles, and which in turn, because the system is interconnected, so we can also have composite body principle. Consider the three-hinge arc shown, which is the only determinate structure. So there are two parts. We can draw free body diagram of segment AB and BC. So in each hinge, there are two unknowns. And since there are two parts, and in each part, three equations of equilibrium can be formulated: summation versus x0, summation versus y0, and summation of moment equals 0. So that means 3 per free body diagram. And since there are 6 unknowns all in all, and there are 2 free body diagrams, so this structure can be analyzed with ease because 2 times 3 is 6, and there are 6 unknowns here. So we can manage to analyze this. So I'll discuss two-force body principle, and this is based on one axiom of mechanics, which states that two forces are in equilibrium only when equal in magnitude, oppositely directed, and collinear in action. So for the segment BC, if the weight of segment BC is neglected, then the reactions at B and C must be equal and oppositely directed because BC is in equilibrium. So to help discuss it, so if this is segment BC, the reaction at C and the reaction at B must be oppositely directed because this member is in equilibrium, then this is a two-force body. So we have R sub B and R sub C. So this is the principle on two-force body, and they are equal for this system to be in equilibrium. So from the second axiom of mechanics, again, two forces are in equilibrium only when equal in magnitude, oppositely directed, and collinear in action. So the reaction at B and C must be collinear, equal, and oppositely directed as shown in the figure. So R sub B equals R sub C. Meanwhile, for segment AB, this is a three-force body principle because there are three reactions, and these forces must close according to triangle law for the system to be in equilibrium. So from segment AB of the arc, since there are three forces in equilibrium, these forces must be concurrent, or we have the three-force body principle. So from reaction, RB should be oppositely directed to this, and we have the reaction at A, which meets with the point where P, the load P, and RB meet for the system to be in equilibrium. So it must close. So the triangle must close. So if we draw the force triangle at O, so we have RA first, inclined up to the right gently, then we have P, then RB must close the triangle. So that's the principle. I hope that you can easily find two-force body and three-force body in a system. And since the body is interconnected, that's also the discussion on composite body principles, where we have to draw free body diagram separately on each part to successfully analyze the situation. Determine the components of all forces acting on each member of the loaded frame. So normally, two force bodies are found in frames. So we'll have more on this on frames when we reach analysis of structures. For the meantime, let's only consider problems where there are two force rigid bodies. So we see that member BC is a two force body because there's no force in between. So R sub B equals R sub C, while segment AB is a three force body because there is a 5 kilonewton load. So the reaction at C should pass through B as well as at B, but B is an internal internal reaction, so we will not show it in the free body diagram of the entire system. So that is R sub C. Since this is 3 and 3, that means this is 45 degrees. So if this is 45 degrees, this is also 1.5. Because segment AB is a three-force body, the reaction should meet to the point of intersection of this 5 kilonewton load and supposedly R sub B or R sub C. So this is 45 degrees also. So that should be the direction or line of action of RA. So to solve for RA, we need to solve this angle also. Take note that this is 1.5 and this total vertical distance is 1.5 plus 6. So this angle is arctan of 1.5 over 1.5 plus 6. So arctan of 1.5 over 7.5, and that is 11.31 degrees. So we set moment C 0 or summation moment about C equals 0, considering vertical component as positive or clockwise moment as positive. So RA cosine of 11.31 degrees times 3 plus 3, so 6 moment arm. The horizontal component is counterclockwise, so minus RA sine of 11.31 degrees times 3. 6 meters minus 3 is 3. Then minus 5 times 1.5 plus 3 is 4.5. So from here, we can now solve RA. The magnitude of RA is 4.249 kilonewtons. Then let's resolve RA into two components. CX RA sine of 11.31 rightward. AX is 4.249 RA sine of 11.31 degrees. So AX is 0.8333 kilonewtons rightward. AY is upward, upward, and it is 4.249 cosine of 11.31. So AY is 4.166 kilonewtons because the question is components of all forces acting on each member of the loaded frame. So before RB and components at B, because the components at B equal to R sub C but oppositely directed. So MA is 0. So we have to consider horizontal component first, which is counterclockwise, vertical counterclockwise. So counterclockwise positive. So equals R sub C sine of 45, the horizontal component times 3. Then R sub C plus R sub C cosine of 45 degrees, the moment arm is 6. 3 plus 3. Then minus 5 times 1.5. So R sub C is equal to 1.1785 kilonewtons. Then Cx equals Cy equals 1.175 sine of 45, and that is also Cy because the angle is 45. So Cx is 0.8333 kilonewtons leftward. Cy is 0.833 kilonewtons upward. So if we consider BC, RB is down to the right. But if you consider member AB, RB is up to the left, which is the same as CX and CY. So therefore, on member AB, BX is 0.8333 kilonewtons leftward and BY is 0.8333 kilonewtons upward. So that's the answer. Those are the answers. Determine the reactions at B and D when B is 120 mm in this figure. So you should be quick in identifying two force bodies. We have member CD is a two force body because there's no other force in between the pins. So let's have RD which passes through C. And because C is an internal pin, then we will not show it R sub C anymore because we consider the free body diagram of the entire system. So we have BH and B sub V only. But take note that R sub D equals R sub C, of course. So by principle of transmissibility of a force, the angle here is 45 degrees because this is a quarter circular arc, arctan of 75 over 75, so 45 degrees. By principle of transmissibility of a force, we move RD to C. So set moment B0. Let's consider clockwise positive. This component of RD is RD sine 45. The moment arm is B, which is 120 mm. So equals RD sine 45, then times 120. The vertical component is counterclockwise, so minus RD cosine 45 times moment arm 90. Then minus 80 times 250. So from here, we can solve the magnitude of RD. RD is equal to 942.8 newtons. So our answer for RD is 942.8 newtons directed down to the right at an angle of 45 degrees to the horizontal. So always put the angle from the horizontal when you answer. Then RH is 0, or horizontal component of resultant is 0. So we have RD, which is 942.8 sine of 45 degrees, the horizontal component rightward, minus BH equals 0. So BH is equal to 666.7 newtons leftward. Then R vertical equals 0. So we have B sub V minus RD 942.8 cosine of 45 degrees, the vertical component, minus 80. So vertical component of reaction at B is 746.7 newtons upward. So therefore the reaction at B is up to the left. The magnitude is square root of 666.7 square plus 746.7 square. So the magnitude of RB is 1001 newtons. Then the angle it makes with the horizontal is arctan of 746.7 over 666.7. Arctan of vertical component over horizontal component. So theta B is 48.24 degrees. Therefore, our answer for reaction at B, because it is a vector, is RB is 1001 newtons directed up to the left at an angle of 48.24 degrees to the horizontal. So this is interconnected system or composite bodies. Calculate the magnitude of the force acting on pin at D. Pin C is fixed in DE and bears against the smooth slot in the triangular plate. So let's consider first the triangular plate. And we have here the reaction components at A, which are not important because we only want the magnitude of the force acting on pin at D. So we have normal reaction at C. This angle is arctan of 120 over 160, so that's 36.87. Then this is F sub C, which is perpendicular to AC. Normal because this is frictionless. Then the angle here is, the measure of the angle here is also 36.87 with the vertical by principle. So considering triangle ABC, we can solve FC by setting MA equals 0 or summation moment A is 0. By the way, the perpendicular distance of F sub C from A is 200 mm, and 200 mm is square root of 160 square plus 120 square. So that's 200 mm. So M sub A equals 0, counterclockwise positive. So we have FC times 200, then minus 100 times 140. So F sub C is equal to 70 newtons. Next, we draw the transmit FC, which is now down to the right. Then we consider this portion DCE. So this is the FBD, same angle, then component reactions at D, and reaction at D, which is just horizontal. So to solve for dH, we set moment E 0, then clockwise positive. So we have equals dH times 120 plus 80 is 200 mm. dH times 200. Then the only component of 70 that has moment about E is the horizontal component. The vertical passes through E. The horizontal component is so minus 70 sine of 36.87. That's the horizontal component. The moment arm is 80. So dH can now be solved. It is equal to 16.8 newtons. Then set R vertical equals 0. So dV equals this V, then minus 70 cosine of 36.87. So this V is equal to 56.00 newtons. Finally, the magnitude of the reaction at D, or force on pin D, is square root of 16.7 square, 16.8 square plus 56 square. So R sub D is equal to, or force on pin D is 58.47 newtons. Compute the magnitudes of all forces on member CDE of the frame. So by taking a look, we have two force bodies, namely BC and VD are two force bodies here. And even AB, AB is also a two force body. But since we are asked for the magnitudes of all forces on member CDE, so it's not important. Important only for computing the vertical component at AE. So let's assume these are the directions of the component reactions at external component reactions at A and E. We can solve E sub V by setting moment A0, considering the whole system, clockwise positive. So this is equal to E sub V times 4 and minus 80 kips times 9. Therefore, E sub V is equal to 180 kips positive, so it's downward. AV therefore is 180 kips upward if you sum up forces vertical. Next, let's consider CDE and apply the forces in the two force bodies BC and VD as shown. So assuming these are the directions, if we made the mistake, then they will just be negative, so it should be opposite. So take note that we have found E sub V. Then we extend FBD here, its line of action, because we plan to set moment here. Call this point O0. So let's call this distance point O, this distance A. Then let's solve for A by similar triangles. A as to 6 equals 4 as to 3. This is 3. 3, 9 feet minus 6 feet. That's 3. So horizontal, vertical, so that's also 3. So same angle. Therefore, this angle is 53.13. Arctan of 4 feet over 3 feet. Arctan of 4 over 3 is 53.13. This is also 53.13 degrees. So A as to 6 equals 4 as to 3. So A is 8 feet. So this is 8 feet. So moment O equals 0, considering clockwise moment positive. There are two components of FBC, namely horizontal. Let's begin with horizontal component, and it is clockwise, so equals FBC sine of 53.13 degrees. The moment arm is 6 plus 6, so 12. Then vertical component is also clockwise, so plus FBC cosine of 53.13 degrees. The moment arm is A, or 8. Then minus EV, FVD and EH are not involved. They pass through O. Minus 180 times A, which is 8. So from there, we can solve FBC. The only unknown in this equation, FBC is equal to F sub C equals 100 kips. So take note that we are just computing the magnitudes. Then vertical, R sub V equals vertical. This is also 53.13 degrees. So set vertical component of resultant in this portion CD is 0. So we have FBC, which is 100 cosine of 53.13 degrees, plus FBD cosine of 53.13 degrees, then minus E sub V, which is 180. So from there, we can solve the force on FBD or FD. So it is equal to 200 kips. Finally, let's solve for EH, set RH 0, and it is equal to EH, or 100 sine of 53.13 degrees, then plus EH, then minus FBD sine of minus 200 sine of 53.13, the horizontal component of FBD. So EH can now be solved. EH is 80 kips. Therefore, the magnitude of the force on E is square root of 80 square plus EV, which is 180 square. So R sub E equals FE equals 197 kips. Knowing that theta is 30 degrees, determine the reaction A at B, then at C. So for reactions at B, it is up to the left, of course. And R sub C, by 3/4 body principle, you should meet somewhere here. So it should be down to the right. And that's 30 degrees. So set MC0 to solve for RB. And by principle of transmissibility of a force, let's move RB here at the center of this quarter circular arc. There are two components, vertical, which passes through C, horizontal, that has moment about C. So let's have counterclockwise positive. This component of RB is RB sine 30. And the moment arm is R. So equals RB sine 30 degrees, this horizontal component. Moment arm is R. Then minus P times also R. So cancel R. RB therefore is P over sine 30. So RB is 2P. Then set RH. RB therefore is 2P up to the left at an angle of 60 degrees with the horizontal or to the horizontal. 30 degrees from the vertical or 60 degrees to the horizontal. We always express direction from the horizontal. So RH is 0. So horizontal component of RC is CH equals CH, then minus 2P sine 30. Minus RB sine 30 or 2P sine 30, the horizontal component of RB. So CH is equal to P, rightward. Then R vertical equals 0. Vertical component of resultant is 0 by equilibrium. So we have RB, which is 2P cosine 30, the component of vertical component of RB. Then minus CV, which is downward, minus P. So CV is 2P cosine 30 minus P, and that is equal to 0.7321 P. Therefore, the reaction at C is square root of P square plus 0.7321 quantity square. Quantity 0.7321 P square. So R sub C is 1.239 P. Since this is reaction and reaction is a vector, it's a force, then theta C is arctan of 0.7321 P over P. Cancel out P. So theta C is 36.21 degrees. So therefore, our answer for RC is 1.239 P directed down to the right at 36.21 degrees to the horizontal. An 8 kilogram slender rod of length L is attached to collars that can slide freely along the guides shown. Knowing that the rod is in equilibrium and that beta is 30 degrees, determine the angle theta that the rod forms with the vertical and the reactions at A and B. So we cannot solve directly theta. So let's have reactions at A and B first. Look at the figure. So since the guides are free to slide, then we have to apply the weight, which is M times G. M is 8 kilograms. G is 9.81 at the center. Then our reaction at A, which is horizontal to the left. This beta is 30 degrees. Then reaction at B is perpendicular to this axis of this rod here, which is of this guide, which is 30 degrees to the horizontal also, and it is perpendicular. So 30 degrees from the 30 degrees from the vertical. So if we draw the first triangle, we have MG. Next is RB, which is the angle between the vertical and RB is also 30 degrees. Angle of depression or angle of inclination, that's the same by principle. Then we have RA horizontal. So we can solve RA in this right triangle, vertical and horizontal. So this is a right triangle, 90 degree here. Tangent 30 degrees is RA over MG, where M is 8 and G is 9.81. So RA is to the left. Magnitude 45.31 newtons to the left. Then cosine of 30 degrees equals mg, 8 times 9.81 over rb. So rb is equal to 90.62 newtons directed up to the right at an angle of 60 degrees to the horizontal, because it is 30 degrees to the vertical, so 60 degrees to the horizontal. We always express the directions to the horizontal. Then the angle, so let's have this distance 0.5 L sine of theta, this one. Then the horizontal distance between this point and A is L sine theta as shown. Then the vertical distance between B and A is L cosine theta, this one. So we set moment B0 and considering clockwise positive, so RA 45.31 times L cosine theta, moment arm, and minus mg minus 8 times 9.81 moment arm, 0.5 L sine theta. So cancel out L, so we have 45.31 cosine theta equals 8 times 9.81 times 0.5 is 39.24 sine theta after transposing. So tangent theta is 45.31 over 39.24. From here, we can now solve theta. Theta is equal to 49.11 degrees. So that's it for this batch of problems.